Welcome back to the series. I am Zeal, an open source contributor to the Agent Governance Toolkit. In episode 1, we built the firewall, which was a policy engine controlling what a single agent is allowed to do in isolation. Today, in episode 2, we are tackling the next major hurdle, securing the communications between those agents. Welcome to Agent Mesh and the Trust Layer. So, here is a roadmap. We'll start with the core problem of agent identity, look at the four-layer architecture of agent mesh, and then dive into how cryptographic identity and 15-minute credentials actually work. Then we'll break down trust scoring and run a live demo on capability delegation and trust handshakes, finishing up with the protocol bridge. In episode 1, we built a policy engine that controls what a single agent is allowed to do. Every tool call gets checked before it runs. That's the firewall. But here's the next problem, and it's one most people haven't thought about yet. What happens when agents talk to each other? Because in real systems, agents don't run in isolation. You have an orchestrator agent spinning up sub-agents. You have a research agent handing off to a writing agent. You have a billing agent receiving instructions from a planning agent. And the question nobody is asking is, how does any of this agent know who is it talking to? Right now, in most multi-agent systems, the answer is it doesn't. One agent sends a message to another and just assumes it's legitimate. There is no identity verification, no way to know if the agent on the other end has been compromised, impersonated, or replaced. That's exactly the problem agent mesh solves. It's the trust layer. Zero trust identity for agents. So every agent in your system has a cryptographic identity, a trust score, and a verified credential. And if an agent tries to step outside its lane or impersonate another agent, the mesh catches it. When we talk about agent mesh, think of it as the nervous system that connects your agents together securely. If Agent OS is the firewall, Agent Mesh is the identity card and the communication channel. These two work together. If Agent OS asks, is this action allowed? Agent Mesh answers, and can we verify who is actually asking? Agent Mesh has four layers. Layer 1, identity and zero trust core. That's where agent identities live. Credentials get issued, and SPIFFE integration happens. Layer 2 is trust and protocol bridge. That's where agents talk to each other securely across different protocols. Layer 3 is governance and compliance, audit logging, EU AI Act mapping, policy enforcement at the mesh level. And layer 4 is reward and learning, trust scores that adapt based on agent behavior over time. Today we are focusing on layer 1 and layer 2, which is identity and trust. That's the core of what the issue asks us to cover. Identity, DIDs, trust scoring, and capability delegation. And for contributors, this architecture is in the packages folder in Agent Mesh. The file structure maps directly to these four layers, which makes it very navigable once you know the shape of it. What is agent identity? What does it actually mean for an agent to have an identity? Think about how humans prove who they are on the internet. You have a username and password, or a certificate or a hardware key. The point is, there is something that proves you are who you say you are, and it's hard to fake. Agents need the same thing, but the traditional approaches don't quite fit here. API keys get leaked, passwords get shared, static tokens don't quite expire, and with agents running at machine speed, making thousands of decisions per second, you need something cryptographically strong and fast. Agent Mesh uses ED25519, which is a modern elliptic curve signature algorithm, plus quantum safe MLDSA65 credentials for future proofing. Every agent gets a key pair. The private key never leaves the agent. The public key gets registered, and every time that agents want to do something, it signs the action with its private key. Anyone who receives that action can verify the signature, and if it doesn't verify, the action gets rejected. On the top of it, each agent gets a DID, a decentralized identifier. It's a unique portable identifier that travels with the agent and can be verified without relying on any central registry. So when agent A sends a message to agent B, can cryptographically verify, yes, this message actually came from agent A. It hasn't been tampered with, and the agent hasn't been revoked. That's zero trust identity. The username password analogy lands well for developers who haven't worked with cryptographic identity before. How credentials work. Now, here is an important design decision in agent mesh that's worth understanding, especially if you're contributing. Credentials are ephemeral. They have a 15-minute TTL by default. Why? Because a compromised credential that expires in 15 minutes does far less damage than one that's valid forever. If an agent gets taken over, the attacker's window is tiny, And the governance layer knows immediately when a credential expires and a new one isn't issued cleanly. That's a signal something is wrong. The flow is an agent starts up, it requests a credential from the agent certificate authority inside agent mesh. The CA verifies the agent's identity, checks its registration, and issues a short lived credential. The agent uses that credentials to sign its action. After 15 minutes, it gets a new one, continuous, automatic, and short lived. And there is one more piece human sponsors. Every agent in Agent Mesh has a human sponsor, a person who is accountable for that particular agent's behavior. That's in sponsor.py. This is a deliberate design choice. You can always trace an agent back to a human who owns it. That's not just a nice to have under the EU AI Act, it's becoming a compliance requirement. Let's talk about trust scores because this is one of the most interesting parts of the whole system. Every agent gets a trust score on a 0 to 1000 scale. Not a simple trusted or untrusted flag, an actual number that moves over time based on the agent's behavior. The tiers are 900 to 1000. It is a verified partner. It means it is cryptographically verified and it has a long track record. 700 to 899. It means it is trusted. It has an established history with elevated privileges. 500 to 699. It means it has a standard trust score, the default for any new agent that registers with a valid identity. 300 to 499. It means it is probationary. It has limited privileges and it is under observation. And lastly, 0 to 299. It is untrusted. It is restricted to read only or blocked entirely. Every new agent starts at 500. That's intentional. You don't start trusted, you earn it. So, what moves the score? Successful task completions push it up. Policy violations push it down. Failed trust handshakes push it down. And the scores feed directly into what the agent is allowed to do. A ring 0 agent with a score above 900 gets full capabilities. A ring 3 agent with a score below 300 is basically sandboxed. You can see the live trust state of your agents with the CLI. Let's start with the demo. First, I'll be installing Agent Mesh. As we can see, it's installed now. After installing the package Agent Mesh, I already created a folder called Demo2 and I'm going to start with Agent Identity because everything in Agent Mesh begins there. Then I'll move into trust handshakes between agents. So this is my file, my demo file. First, I'm importing Agent Identity and this is the core object that gives an agent a cryptographic identity inside the mesh. Now I create a new identity for a research agent. I give it a human sponsor, which is important because every agent in the system is accountable to a real person. I also define its capabilities. In this case, it's read data and write reports. Next, I print the basics, which is agent name, its DID, its status, its sponsor, and its capabilities. The DID is the decentralized identifier for this agent. This is what other agents use to recognize it. Now let me show you signing and verification. I create a message which is requesting access to user database. The agent signs that message with its private key. Then I verify the signature against the original message and that should return true. Now, I test a tampered version of the message which requests access to admin database. Same signature but different message. Verification should fail here. That's the core security guarantee here. If the payload changes, the signature no longer matches. After that, I demonstrate capability delegation. In capability delegation, the parent agent creates a child agent and only delegates read data. So the child is narrower than the parent. I print the parent DID, the child DID, the child parent's DID, delegation depth, and child's capability. Then I explicitly show that the child cannot write reports. Finally, I try an escalation attempt by delegating admin all, which the parent does not have. That raises an error, and that's exactly what we want. Delegation can narrow permissions, but it cannot create a new authority. Now let's run the program. So first you can see the agent name is research agent. It gets a DID, which is its decentralized identifier inside the mesh. The status is active and the sponsor is this, which means the agent is tied back to a real accountable human. It also has two capabilities, which is read data and write reports. Next is signature verification. I take the message requesting access to user database and sign it with the agent's private key. You can see a signature is generated, and when I verify the exact message, it returns true. That means the message is authentic and has not been changed. Then I tried the tempered version of the same message. The script changes it to request admin database access instead. Now verification returns false. That's the key zero trust property here. Even a small change to the payload breaks the signature. Let's look at capability delegation. The parent research agent delegates a narrower scope to a child agent. The child gets its own DID, and you can see its parent DID points back to the original agent. The delegation depth is 1, which means this is the direct child. Most importantly, the child only gets to read data. To prove the scope was narrowed, I checked whether the child can still write reports, and the answer is false. So, delegation in agent mesh narrows authority, not expands it. Finally, I test an escalation attempt. I try to delegate admin all, which the parent agent never had. So the system rejects it, which cannot delegate capability admin all, not in parent's capabilities. That's exactly what we want. An agent can only pass along permissions it already owns, not only as a subset. So at this point, we have shown three things: identity, message signing, and scope delegation. Next, I'm going to show the trust handshake, where one agent verifies another agent before any communication is allowed. So now I'm opening handshake-demo.py file. In this file, I import trust handshake, agent identity, and identity registry. I use the registry as a simple source of truth for which agents are known and active. Then I create three agents: a research agent, a billing agent, and a sandbox agent. Instead of putting trust scores directly on the identity model, I store them in a separate trust score map. That's cleaner architecturally because identity and trust are related, but they are not the same thing. In this demo, the research agent has 760, billing has 820, and sandbox has 420. Then I register all three agents in the registry. Next, I create a handshake object for the research agent. This is the agent that's initiating trust verification with its peers. The first test is the success path. The research agent tries to establish a trust verified connection with the billing agent, requiring a minimum trust score of 700. The second test is the failure path. It tries the same thing with the sandbox agent, again requiring a minimum of 700. So let's run the file. So as you can see, the first section is trust handshake, trusted peer. Here the handshake is verified as true. The peer DID shown is the billing agent. Its trust score is 820 and its trust level is trusted. Because the billing agent is above the required minimum score of 700, the handshake succeeds and communication is allowed. You can also see the latency in milliseconds, which allows how fast the trust check completed. Now look at the second section, which is the trust handshake low trust peer. This time the handshake is verified as false. The peer DID is the sandbox agent, and the rejection reason is the trust score 420, which is below required 700. That's the key idea behind the trust layer. A peer can be real, registered, and cryptographically valid, but still not trusted enough for a particular interaction. So, trust is not just identity. Identity answers who the agent is. Trust answers where the agent should be allowed into this conversation. So across these two demos, we have shown the full 2 episode core flow. So first, every agent gets a cryptographic identity and a DID. Second, messages can be signed and verified, and tampering gets detected immediately. And third, capability delegation is scope limited, so child agent cannot escalate beyond their parent. And fourth, inter-agent communication is protected by a trust handshake, where peers must meet a required trust threshold before any exchange is allowed. Also, if you type this command, agent mesh trust report, you can see the various agent and its level. As I mentioned earlier, it is verified partner, trusted, probationary, and untrusted. So you can see the success, failures, and the activity with the score. One more thing which is worth covering is the protocol bridge. It is in the location trust folder and in the file bridge.py. And it's what makes agent mesh work across different agent ecosystems. The reality is that not all agents speak the same protocol. You might have agents built with LangChain, agents using Google's A2A protocol, agents using MCP, and agents using IATP. In a real enterprise system, these all need to communicate. The trust bridge handles the translation. It takes a trust verified message from one protocol and translates it to another while preserving the cryptographic guarantees. The identity verification doesn't get lost in translation. For contributors, this is one of the most active parts of the code base. New protocol adapters are being added regularly. If you want to contribute, a new protocol bridge is a well scoped, well defined contribution. So let's map this back to the OWASP Agentic Top 10, which I also talked about in the previous video. First is ASI03, which is Identity and Privilege Abuse. That's exactly what we just built protection against. Cryptographic identity means you cannot impersonate an agent. Capability delegation with scope chains means you cannot escalate privileges. ASI07 Unsafe Interagent Communication. The trust handshake and encrypted channels address this directly. Agents cannot communicate without mutual identity verification. Lastly, ASI10, which is rogue agents. Trust scoring combined with the kill switch from the runtime layer means a rogue agent gets flagged. Its score drops, its access is restricted, and if it keeps misbehaving, it gets terminated. Quick recap. We started with the problem. Agents in multi-agent system have no way to verify who they are actually talking to. Then we looked at what agent identity actually means. ED 25519 key pairs, DIDs, ephemeral credentials with a 15-minute TTL, and lastly human sponsors. We walked through trust scoring, which is scored from 0 to 1000, and a new agent starts at 100 and behaviors move the agent score. We wrote the code, created an identity, signed and verified messages, delegated capabilities with scope enforcement, and we looked at the trust handshake and protocol bridge for secure cross agent communication. If you want to contribute, the identity layer is in the packages folder inside agent mesh, inside the source folder where you get the identity folder. And the trust layer is in the trust folder, and the ADRs in the document folder, which explains why specific design decisions were made. The delegation chain logic and the protocol bridge are both areas where contributors can make a real impact. Next video is episode 3, which talks about agent SRE and observability, chaos experiments, SLO monitoring, audit logging, replay debugging. How do you know your agent system is healthy? And what do you do when it is not? That one is going to be an interesting one. See you in the next video.